This is the first Resonate webinar today. We're going to give it 1 or 2 more minutes before we kick it off and give people a chance to join. And then we're going to talk about distributed async await and especially have few demos of the brand new Python SDK. See the Python SDK in action. So should be fun. All right, let's give it 1 more minute. Or maybe half a minute. Next time, we need to cue some music. Do some fun music. Then nobody's bored. While we wait for more attendees. All right.
We have some people saying hi in the chat.
Oh, fantastic. Thank you very much for letting me know. I need some hand holding here because I am totally new to Riverside. And if Thomas didn't mention that, I would actually not have seen the chat window. Thank you very much. Hey, hello, everybody. Thanks for joining. All right. So then, speaking of being somewhat new, to this app, let me see, did I share the right window? Okay, cool. All right, then I'd say we can get started. Okay, so once again, hello and welcome everybody to our first webinar. Thanks for being here with us today. So this webinar is live streamed and will also be recorded. And if you joined the webinar via the invitation link, please feel free to post some comments and questions in the chat, and we'll do our best to answer live right here and now. So I'm your host, Dominic Torno. I'm founder and CEO of Resonate, and with me here today is Resonate team, David, Andres, Thomas, and colleague. And so today we're gonna hear from a bunch of us. I will give a brief conceptual introduction to Resonate because I cannot resist conceptual introductions. So it's like short conceptual I will keep it brief. Short conceptual introduction to Resonate, and then we'll explore a few demos. I'll have a distributed calculation of the factorial numbers, and then Kali is demonstrating a workflow that shows human in the some human in the loop steps, and then Thomas is going to show us a workflow that demonstrates some batch processing steps. So for the conceptual introduction, and again my favorite part, I'm going to be talking about distributed async await. So building modern cloud native applications is characterized by its inherent complexity. Right? And at Resonate, we focus all of our efforts on reducing that complexity. So our goal is to make modern applications dead simple. And distributed async await is a programming model for building concurrent distributed applications that offers a delightful and dead simple developer experience based on functions and promises. And for us, dead simple is not just a catchy phrase. Dead simple is at the center of our technical values. We aim to be dead simple to understand, dead simple to develop, and dead simple to operate. Now today, every application is a distributed application. So think of mobile applications, think of cloud applications, or think of microservices. So today the question is not if an application is distributed, but only to what extent an application is distributed. Distribution is a fundamental aspect of software engineering. Now that shift has enabled unprecedented scalability and unprecedented reliability, but it has also introduced daunting complexity. So we have to deal with the added challenges introduced by fragmentation, by computations that are distributed across space and distributed across time. Distribution across space and distribution across time introduce challenges that can be traced back to two defining characteristics of concurrent distributed systems: partial order and partial failure. The defining characteristic of concurrency is non-deterministic partial order of executions. In a concurrent system, we simply do not know what will happen next. The defining characteristic of distribution is non-deterministic partial failure. In a distributed system, we simply do not know what will fail next. So let's consider a simple example. Two processes, P and Q, each consisting of just 3 steps. The concurrent composition of P and Q leads to 20 distinct possible executions. The distributed composition of P and Q leads to 69 distinct possible executions. And now imagine the behavioral space of real-world distributed systems with dozens or hundreds of processes, and each with dozens or hundreds of steps. Now, this table is my favorite conceptual framework. It presents a conceptual framework to reason about the challenges that are introduced by concurrent distributed environments and the countermeasures that we employ. Concurrency introduces non-deterministic partial order. And to mitigate the uncertainty introduced by partial order, we employ coordination. And distribution introduces non-deterministic partial failure. And to mitigate the uncertainty introduced by partial failure, we employ recovery. Now, different programming models have been created to elevate concurrency to a first-class citizen. And arguably the most popular programming model, implemented in languages like JavaScript, TypeScript, Python, C#, F#, or Rust, is async await, a programming model built on functions and promises. Now, distributed async await is an extension of async await and elevates distribution to a first-class citizen. So async await, the classical async await, formalizes the concurrent structure of local computations and does not at all concern itself with recovery. And in contrast, distributed async await formalizes the concurrent structure of global distributed computations and additionally does formalize recovery. Now, given what we know about async await, what extension do we need to make distribution and recovery first-class citizens? Now, functions and promises are composable universal abstractions for computation and coordination. Right? Do some stuff and wait for some stuff. That is the lingua franca, the universal language of software systems. When the caller invokes the callee, instead of waiting for the result, the caller immediately receives a promise while the callee executes concurrently. A promise is either pending or completed, more specifically resolved or rejected. If a promise is pending, the promise is unfulfilled and the execution is still ongoing. And if a promise is completed, the promise is fulfilled and the execution has already concluded, it has terminated. When the promise is resolved, that indicates success, and the promise is rejected, that indicates a failure. Now the caller and callee are able to coordinate their execution with the caller waiting for the promise and the callee completing the promise. So now, given what we know about async await, what extension now do we have to make distribution and recovering first-class citizens. We need durable promises. Durable promises are, and here we go again, they are dead simple. Yeah, durable promise has a unique ID, a URL, and it stores its value in durable storage. And that's it. That's all we need. That simple concept forms the very foundation of a concurrent distributed programming model. By assigning a unique ID, promises can be used to coordinate executions across processes. And by persisting its state, promises can be used to recover an execution regardless where it may have failed. So in effect, there is a dead simple programming model, distributed async await, based on functions and promises, running on top of a dead simple environment, the distributed event loop. Now, let's look at an example, calculating the factorial. Okay, now, calculating factorial is not the canonical use case for showcasing concurrency and distribution, because generally there's no concurrency and there's no distribution. But it is the canonical example for demonstrating recursion, composition. Yeah. So in this case, and we will look at actual code later, not code on the slide. In this case, factorial invokes itself locally. You see here LFC, short for local function call. Factorial involves itself locally, recursively. And that is significant because it shows that in Resonate, there is no separate concept of something like a workflow and actions or a workflow and activities. There is not this two-step separation. There are only functions and promises, and they compose recursively. You can build even the largest system from the smallest building blocks, from just functions and promises. And factorial illustrates that nicely because every single call to factorial adds yet another execution. Now, this is the async call graph of the invocation of the code that we just saw that calls factorial only locally. And again, the call graph is non-concurrent and non-distributed because every single call is a local call and it awaits immediately. Right? It does not kick off yet another call so that they run concurrently. No, it awaits immediately. Now here above the line, the diagram illustrates the logical layer. Right? The logical layer is characterized by the concurrent and distributed structure of a computation. And below the line, the diagram illustrates the physical layer, characterized by the assignment of execution to nodes. So the gray boxes on the bottom show potential nodes where an execution may be hosted, may be executed. In our case, everything from factorial 3, 2, 1, and 0 runs on one node, guaranteed, because we called every single function locally, LFC. Now let's look at this example. In this example, instead of calculating the factorial locally, we calculate factorial remotely. Here, illustrated with the method RFC, remote function call. So every step of the calculation is scheduled by the global event loop on a different node. Possibly every single step runs on a different node. So here we see the async call graph, which is still non-concurrent. It did not change that, but is now distributed because every single call happens remotely. And now a possible execution is where the factorial of 3 runs on one node, the factorial of 2 runs on another, factorial of 1 runs yet on another, but as chance has it, the factorial of 0 runs on the same node as the factorial 3. But the important part is that the execution and coordination is now managed by Resonate's global event loop. Now, you may ask yourself, okay, what is assignment function? How do we determine where to run an execution? Well, Resonate has what we believe is a sensible and also very simple to use default, but in future iterations of Resonate, we plan on making that particular aspect of Resonate programmable via simple plugin architecture. So you can also plug in your own assignment logic, therefore basically using Resonate as a custom job scheduling platform. Now, and of course, you can mix and match, right? So in this example, every time we like every odd, yes, every even number, we call factorial remotely, and every odd number we call factorial locally. So in that case, this is the async call graph. Here we see factorial 3 and factorial 2, since they're connected by a local function call, being guaranteed scheduled on the same node, being coordinated and executed by the local event loop. Right? But then the relationship between factorial 2 and factorial 1 is that of a remote function call. So there the coordination and execution is facilitated by the global event loop, by the Resonate server. Now, and once again, the assignment is now that factorial 3 and factorial 2, they're guaranteed to run on the same process, but then factorial 1 and factorial 0 may end up on a different process. Now, the protocols that are involved to make the distributed event loop work are two protocols that are layered on top of each other: the distributed coordination protocol and the distributed recovery protocol. But that, I think, would go too far today for a conceptual introduction. So if you are interested in the ins and outs of how these two protocols mitigate concurrent or partial order and partial failure, I recommend to check out my P99 conf talk about distributed async await, where we look into the details of the Resonate server architecture and then also the protocols that drive Resonate. And now let's have a quick look at the actual system and some of the code of the system. For that, I need to do some rearranging. And I think we are there. Okay. All right, cool. So here we basically see the same code that we saw on the slide. We have the factorial, and the factorial is the classic factorial implementation. Here we stop the recursion, and here we call the factorial remotely via the RFC. We instantiate a scheduler and register the factorial. So here I'm using Resonate's low-level API. For the next release of Resonate, we also give it some of the quality of life improvements and a high-level API, so that, for example, in Python, you can simply use decorators to register and call functions. Anyways, as you see here, we just accept we just accept a number to calculate the factorial with on the command line, and then we run the factorial. So what we do here is we give the promise that represents the factorial a fixed name. So for example, factorial 5, factorial 4, factorial 3. We also do that here. And as you can see, I am messing around with target nodes, right? So if you use the default out of the box experience, then generally the assignment you do not need to worry about assigning names, for example, or group identifiers to the different nodes that are at play. Why am I doing this? Because I would like you to see that the factorial neatly jumps from left to the middle to the right and left to the middle to the right. So I'm using a custom naming scheme here. If I didn't do that, we would basically just see the factorial being assigned to processes randomly. And because the factorial is not actually like consuming any resources, there's a good chance it all would just happen on a single node. So I am messing around a bit with the assignment function so that we see it just like the cool effect. All right, so now I'm starting the same script on each and every server, so to say, each and every server, and it accepts any of the servers accepts the like a factorial to calculate for. I want to calculate factorial 5, right? So now what I want to see is that we calculate factorial 5 on the left and factorial 4 in the middle, factorial 3 on the right, and then we keep going that way. All right, so we're calculating factorial of 5 on node number 2, factorial 4 on node 1, factorial 3 on node 0, and then we go all the way back, calculate factorial 2 on node 2, calculate factorial 1 on node 1, calculate factorial of 0 on node 0, and eventually we get the value. So we're building the call stack, right? And then eventually we are bringing down the call stack again, and then we calculate the value of factorial of 120. So now to check on the durability, right? What happens if I request the factorial of 5 again? Well, remember that we use stable identifiers, right? And I said what the identifier is going to be. I said the identifier is factorial 5. So that promise and the result of that promise is durably recorded. So if I do that, it's already done, right? So the system is not going to calculate that again. It is simply returning what it already calculated. Now that is true obviously for 4, that is true obviously for 3 and all the way down. But what happens if I now want to calculate factorial 6? Are we going to see some remote function call? Well, actually no, because we calculate factorial number 6 right here, and then when we request factorial of 5, that has already been done. So then we immediately return that. Now, if I request factorial of 8 now here, then the same would happen. So therefore, I request factorial 9 so that we can see it jump at least once. And then we see it jump to the other side and come all the way back to the node 2 here again. Okay, so for the last one, and I'm gonna restart the server. I gave the server I stored in memory. So therefore, if I restart the server, right now all the promises are wiped from the memory of the server. So now we can start again, and let's do that. Just for fun. Okay, what is that going to do? So on the factorial 2, we do what we said before. So it's like if it's an even number, right? If it's an even number, we calculate locally, and if it's an odd number, we calculate remotely. Actually, I think that was just the other way around in the presentation. But anyways, so here we're gonna call the LFC, the local function call. Here we're gonna call the RFC, And so we basically only going to see the factorial hop at every other call. So, all right, that's going to be an off by 1 error, but let me think about it. So if we request factorial 6 here, then factorial 5 is going to happen on the same node right away, local function call. And then we're going to go to the middle with the factorial 4 and then the factorial 3. And then we're going to go one further with factorial 2. If I'm not mistaken. We'll find out. We'll find out. So if we do factorial 6, then yes, factorial 6 on node 2, 5 on node 2, 4 and 3 on node 1, 2 and 1 on node 0, then the 0 on node 1, and then once again. So that shows us the mix and match capability. And what I want to draw attention to, what I think is really, really cool about this is, so first off, we're not trying to be smart, all right? We are not trying to pretend that the distributed system is not a distributed system. You are in control, and it is your responsibility to decide, do you want to run something locally or do you want to run something remotely, right? So you may want to run something remotely in order, for example, for fan-out scenarios, right? You have a job that consists of 10 substeps, and you want to distribute these 10 substeps across 10 machines, right? Then you are the one saying that, oh, I want to run this remotely. On the other side, a workflow may consist of, for example, downloading the contents of a web page and then summarizing it with LLM. You probably want to run that on one machine, right? Because if you already download the data to that machine, you also want to summarize it to that machine, right? It's like, that is not smart if you download it somewhere and then within your cluster transfer that data somewhere else to summarize it over there. So we're not trying to figure any of that out. So that's why we give you two methods, LFC, RFC, local function call, remote function call. And however, after that, it's the same, all right? The local function call returns a promise. The remote function call returns a promise. And you just await the promise. Whenever you want the value, you await the promise, right? So the semantics are unified. You decide where you want to run stuff, but afterwards the semantics are unified. So here, this looks very similar, right? This is actually, it looks the same, except the LFC and RFC part, once again here, the very explicit mention of where to run this. And so for this particular case, right? It's like this is one of the strengths of this programming model. This is the homogenized semantics between local function call and remote function call that you see here. Okay, and once again, if you are interested how Resonate actually manages the remote function call, what happens if a remote function call is invoked? What happens if I wait on a promise that is being fulfilled by a remote function call? Highly recommend check out the P99 presentation that details the protocols and also looks into what happens if one of these nodes crashes and when we have to repair the call graph. Okay, at that point, I already consumed half the time and hogged the microphone. So thank you very much for listening to my part. And then I hand it over to Kali. Kali, thank you very much for checking out the human in the loop.
Awesome. Thanks, Dominic. We do have an interesting comment from Edmondo, who says, sounds a lot like Ray from Anyscale. And I'm not familiar with it. I did pull it up, and it is something interesting to take a look at.
Yeah, so I also took a look. I think it's, there are a few frameworks in Python where you can have a decorator and say, this function must run on a machine that has this GPU, these capabilities. So yeah, I will say it's similar in the sense that you can have like groups of different hardwares where you want to run stuff. But we also not only give you the distribution, we also give you the recoverability of the process if the thing crashes. So it's, yeah, we can distribute the stuff, and in that sense, I will say it's similar. I think another similar framework is Model. Dominic, you mentioned Model before on one of our talks, I think.
Yes, definitely. Again, every single application nowadays is a distributed application. So any application has the need of dealing with aspects of distribution. What we are trying to do, and I do not know Ray framework and Ray remote, so I'm gonna check it out right after the webinar. So anything that I say now does not at all, or may not at all, apply to them. So what we are trying to do is basically have a general purpose programming model that does not only elevate concurrency as a first-class citizen, but also elevates distribution to a first-class citizen, right? And the introduction of concurrency primitives as first-class citizens into our programming languages happened, I would argue, sometimes around the 2000s, right? And I would also argue we are basically overdue for a programming model that elevates distribution to a first-class citizen. So we are looking at the distribution aspect, and a very important part of our technical philosophy and also the tech stack is that we are built on open specifications. So our protocols are open and implementable. Our protocols themselves are dead simple, right? A promise, for example, a durable promise, we have the durable promise specification already published. And that has basically four methods, right? There is a create, cancel if you don't want it anymore, a resolve and reject. So it's very easy to implement that. And also the distributed coordination protocol only exchanges two messages. That's an invoke and a resume. This is our lingua franca to coordinate executions across machines. And then we have the recovery protocol, which itself also is only composed of a few messages. The distributed coordination protocol runs on top of the distributed recovery protocol. So all of that is our open specifications. Only the durable promise standard or durable promise specification is currently published. We're still working on the others while we're implementing it. It's supposed to be an open programming model, and also very important, there is no central element in our tech stack. Right? There is no central server. It's not a star architecture or something like that, where every single component needs to talk to this one and only bespoke server. No, it's also a fully decentralized architecture where a distributed workflow can run across any number of basically durable promise servers. So that's a heart of our programming model, a true open programming model with no central element in it. That's basically what we are shooting for. Again, cannot say what Ray shoots for or does not shoot for. Gonna have a look. So.
Awesome. Yeah, I'm happy to pick it up from here and do a demo of Human in the Loop. I think that
one more. I'm sorry for that, Dylan. I just see your question. I'll address that right at the end of the, so that I don't cut you off again. I'll address that right at the end.
Awesome. Okay, so I'm gonna share my screen here. And the demo I'm gonna do here is showcasing the very common problem of having a human in the middle of your workflow. Basically, you need input from a human right in the middle of your workflow. The very specific use case that I've built up here is pretending that we've got a longer workflow, and at the very beginning, in order for it to continue, the user needs to confirm their email address. So we have this quote unquote workflow. Hopefully folks familiar with durable execution will find this architecture I've created very familiar. You've got a workflow here with multiple steps. The very first step is to send an email to the user, and then the entire thing is blocked, waiting until that user confirms their email, clicks a link in their email, right? Which then would hit an API server, and then the rest of the sequence would continue somehow. The problem with this, right, the biggest issue I think that developers face, one of them, is that they just have no idea how long it will take for that user to confirm their email. And so there's a lot of rabbit holes that folks go down architecting systems that can take the first couple steps and then suspend for some indefinite amount of time, and then figure out how to pick it back up and continue on after that event has occurred. What I think is really great about Resonate, obviously a lot, a lot of the modern durable execution platforms, and particularly Resonate, is you can define your entire sequence in a single function and await each step as it goes, right? And so what we're going to do here is we're going to spin this up as, I think a lot of folks will find this similar to probably a worker and sort of a traditional externally orchestrated situation, like using an external orchestrator. And we'll have two services and basically the workflow workers, if you will, running. So we've got an HTTP gateway where we will accept requests. And the first one, we've got a start method that's going to kick off the workflows with an email. The promise ID is workflow-email address. So basically, each invocation will correlate to a very specific ID, right? And then the other route we've got is this confirm. So once the email is confirmed, it will always be confirmed as long as that durable promise persists. And then we have a very simple email service that mimics sending an email. Super simple. Okay, so let's jump into the demo here. I'm going to run the gateway here. Oh, wait, I'm sorry. First, I'm going to run our server. So we're going to run the Resonate server because this is using all remote function invocation. So our server is running. And now our HTTP server is running. Then we're going to run our email service. And then I'll spin up a application node, which some people might recognize as a sort of a worker, if you will. Not required to set it up in this particular architecture, but it is a familiar pattern I think folks are familiar with, this sort of service-oriented layout, where a request will go to the Resonate server first, and then the Resonate server will invoke and resume. And up here, we'll send some, I think I've start, yeah. Okay, so we'll do test email test1@example.com. This is a user starting the workflow. We can see the workflow started. The email service sent an email. The email was sent, and so now we're at this right here. The workflow is now waiting on confirmation, basically on this to resolve. We need this promise to resolve to unblock the workflow. Resonate makes that just very incredibly straightforward in this very simple example where we can send a confirmation request to the gateway, which then resolves that promise and unblocks the workflow, continuing on to the next steps, however many steps you need. Very cool. I actually did a little dance when this worked for the first time. I'm not lying. It was really cool. So that's great, right? What happens if the workflow goes down, right? While you're waiting on that confirmation. This is what's really cool is that basically the whole thing's suspended. So let's start another one here. Starts. We can kill it. Then maybe the user confirms. The promise is resolved. We bring the workflow back up. The application node comes back up. And we get the resume message from the server, just like that. Dominic already demonstrated a bit of the distribution aspect of Resonate, but let's do that again here, running another application node with the same workflow code on it. We'll start 1, 2, 3 more. And you can see this picked up user number 3. But again, let's say this one's having problems. Oh, it crashes. And then user confirmations come in. And it just resumes, picks right back off. And you can see it will reprint logs. It's replaying, but it's not doing the computation again. It's not actually sending another email. You can see down here, there's no new email sent. It's not like the function is being re-executed. The results are being pulled from the durable promise during a sort of replay. And we'll completely resume on this other application node. All done. So yeah, I think that's a really common use case we see, right? With humans in the loops and solving for that and being able to just write a sequence in a single function and know that at any point this could suspend indefinitely and be brought back up and resume or recover on a completely different application node, even with a human in the loop. So yeah, that was the bulk of what I had planned for this demo, and I'd love to know if there's any questions.
Super cool. I just want to add there is a concept in I want to say especially cloud computing, right? And that is compute storage separation, right? Where we have compute on one node, storage happens on another node. I like also the term for what Cully showed is execution runtime separation, right? Because we have this async call graph, and all of the nodes, you can have the mental model that all of these nodes basically form or compose into one virtual runtime, right? And you saw that, for example, Cully crashed one node, it came down, right? But it then just executed the next step on another node that was available. So all of these individual runtimes compose into one virtual runtime, right? So you can basically have this mental model of execution. There's your logical execution, your sequence of steps that Cully showed in code. There's your execution runtime separation. I like that mental model a lot.
Thank you. Appreciate the opportunity to show everybody that.
Super cool demo.
Thank you.
Awesome. Should I present now the batching or?
Mm-hmm.
Yeah. Okay. So yeah, this example is basically just showcasing batching. I hope this feature you find that very valuable because it's a way for our developers to basically batch stuff horizontally. Like you have multiple concurrent execution of the same use case. And instead of doing like one API call for each one of those use cases, you can batch horizontally and take advantage of performance and I mean, if the server you're talking to is not very resistant to multiple requests, there's less likely you crash that other service. So yeah, let me see if I can share. Oh, I think I have to reopen. Should I still present it, or should anyone take it from here? I don't have like enough permissions to share a screen.
I think if you drop and rejoin and add permissions on the Mac.
Okay, one sec.
First time with Riverside for all of us, I think.
Yeah.
Something I didn't think to try out beforehand. You're muted, Dominic. There you go.
Yeah, I just noticed that. Thank you. Yeah, who doesn't love Mac permissions? Yeah, it has to happen at least once. Oh, naming things. That's right. But also AV permissions. Exactly. Very nice. So that gives me a chance to answer Dylan's question. And so Dylan asked, what is the point of using the local function call with Resonate? Is it local durability? That is, if my local job fails, we cache the intermediate results. That is exactly right. So with the local function calls, right? Wrapping local function calls also in durable promises, basically, that allows us recoverability, right? So it aids our recovery protocol. Now, in theory, all that you need is a very top level, very, very top level promise, durable promise, because that is the indicator of, or that is the restarting point, so to say. But with the individual promises that you create along the way, every single durable promise allows you to jump ahead. Right? So if your functions are idempotent, which they have to be, you can also say, I do not want to create intermediary or at every single step an intermediary durable promise. Yeah, that is a configuration option. So now you can trade throughput with or latency with durability, right? Because of course every durable promise adds a network call, and if you forego durability, then you don't need that network call. But if you then if the node crashes and you have to restart, you basically go back further into the past. So that is a knob that you have that you can dial. But the basic idea, yes, you can. If you use the local function calls only, of course there won't be any distribution, but you still get the recovery properties.
Okay, sorry about that, guys. Yeah, so in this example, let me do a little zoom there just to make that easier for you guys to read. This is how you will normally define like a sequential insertion using Resonate. So this is a local function invocation of this function. And this function is basically just an insertion into a database. Doesn't really do anything more than that. And yeah, we are doing a commit every time we call this function. So this is like the most straightforward and likely how most people have it. So they will have like well, in my experience, they will have like an HTTP endpoint, and then there's one commit on every endpoint handler in their web server. The thing is, if your application becomes popular, you'll have multiple concurrent users hitting all those endpoints. You will have end users and commits on the database. With Resonate, we want you to be able to take advantage of batching, not only like on a sequential manner. That's like the easy way when you have all the data you need available on the same, on the same use case. But also, if those use cases are happening concurrently, then you can batch all together without needing to coordinate yourself, because we are going to coordinate all the data needed for that on the SDK side, and then you take advantage of batches. So yeah, just to make an explanation here, you haven't seen, so far in the demo, you have seen context, local function call, and RFC. So this is basically a local function invocation which returns a promise, and then you yield the promise to await for it. The LFC is basically like syntax sugar that immediately waits for stuff. If you need something to be awaited immediately. But in this case, just for the sake of the example, I added like these two in separate steps. So the thing is, you have these as your handler. Then you do a local function invocation of this function. You pass the value, and then you await for it. If you want to have batching, then it's very similar in the sense that you still need to define your use case here. But instead of yielding a function pointer, you yield a data class. You yield a data structure that contains the command needed to be to have it batched. So you will register the data structure alongside with the batch handler in the Resonate or the scheduler level. So the scheduler knows that all these concurrent use cases that are happening, which are yielding this type of data structure, the scheduler can buffer all of those. And then when you await on any of those use cases, then the scheduler will flush as many as it has buffered so far. And you will be able to, well, this list might be possibly like instead of one commit every, if you have, this list can be of any length, really. Of course, there are a few endpoints that have limit, so you can have max length set it here. So if your endpoint or your database for some reason only allows for a given number in a batch, you can set that as a configuration. So just to showcase the power, and this is something that likely if you have followed us on YouTube, you have already seen, but here, if we were to do, where is that? 1,000 sequential insertion into the database. This is 1,000 commits to the database. It takes like half a second. But if we were to use that as batching, since we're buffering all those commands, it takes like 5 times less. So yeah, the key is, as developer, you still feel you're writing sequential looking code. You don't need to bother about coordination across concurrent use cases. We will do all that for you. And you still take the advantage of batches against whatever storage or API you're using.
Super cool. Super cool. Thank you very much, Thomas. I want to say that we want to take all the credit for that idea. Unfortunately, we cannot. So I'm going to drop a paper recommendation in the chat. It is a paper about a library developed at Facebook, Haxel. The paper is called "There is no fork: An abstraction for efficient, concurrent, and concise data access." And that is, by the way, Thomas, I believe you're still sharing the screen. I'm not sure if that was your intention or not, but yes. So that was the paper. And it details that idea and some mechanisms of how you can basically write concurrent code, right? Code that is not coordinated, but have the platform coordinate the executions in order to give you a chance to batch. And on our roadmap for the future, so what you saw right now was the Resonate, the Python SDK, being able to batch local invocations, right? To batch local invocations in future incarnations and future versions of Resonate. We also want to give you the opportunity to specify server-side batches, so that then multiple invocations, if you have a distributed call graph, multiple invocations on the server get batched together and get delivered to one node in a batch. And on that node, they basically simply call the normal executions, which is already batch enabled. So therefore, you actually get also not only local batching, but you get global batching in the first step, and then local batching in the second step. So without any line of code for any coordination, whether global or local, you can actually define different batches. So now that concludes the very first webinar of Resonate. Thank you very, very much for joining, everybody. Thank you very much for the participation in the chat. Thank you, everybody, for being like also the participants for like welcoming and friendly attitude. So please, if you have not, join our Discord, and let's keep the conversation going. If you have any comments, feedback, or question, and then if you do not mind, I'm gonna round this out and share our GitHub repo for the Resonate server, and then also the GitHub repo for the Python SDK. So if you have a chance and start the repo, that would be fantastic. And then thank you very much, everybody. I'm looking forward to the next time, looking forward to chatting with any of you. If anybody wants to chat one-on-one, let me know. Happy to chat and do some brainstorming, a design session, or architecture session. And then the recordings will be posted on YouTube soon. And with that, yeah, thank you very much. And then we see you next time. And thank you, Kali. Thank you, Thomas, for the demo. And David and Anders, thanks for joining.
Thank you. Thank you, guys. Bye, everyone. Bye.